In this video for Chapter 17, we're going to start into our last main topic for this chapter, which will be broken up into a couple of videos, and that is the topic of solubility. And solubility works a lot like how we've dealt with weak acids and weak bases. So we have a constant, which is called the solubility product constant, or Ksp. So we dealt with K, we dealt with Ka and Kb, Kw, now we have Ksp. Lucky for us, Ksp, the definition equation for Ksp is exactly the same as all the other Ks that we've done. Okay, so when we're dealing with solubility, we're talking about things dissolving, so a solid becoming ions. So the definition reaction is the solid dissolving. Okay, so we're going to take a solid and we're going to break it up into its ions. We're going to dissolve the solid. So if I have something like zinc hydroxide, some solid zinc hydroxide, it actually makes an equilibrium with its ions. Now you might be thinking, if you're keeping your solubility rules in mind, you might be saying, wait a minute, zinc hydroxide is not soluble. Well, in reality it is, but to a very tiny amount. So the Ksp for zinc hydroxide is 3 times 10 to the minus 16. Okay, so keeping in mind our evaluation of the magnitude of K. Remember, if K is very large, only the forward reaction is happening. If K is very small, only the backward reaction is happening. So K being very small, so 10 to the minus 16, means that only the reverse reaction is really happening to any appreciable amount. So pretty much everything stays as solid zinc hydroxide. But a tiny, tiny, barely measurable amount does actually become zinc and hydroxide ions. Okay? So this means that the solid formation is highly favored. Right? Because of the magnitude of K. So thinking about it in those terms, we can reverse this reaction and talk about the K for forming the solid. So if I have zinc ions plus hydroxide ions making zinc hydroxide, right? Remember what happens when we reverse a reaction, we take the inverse of K. So the K for this reaction is 1 over Ksp, which equals 3.3 times 10 to the 15. Okay, highly favored. Right, so when you put zinc ions and hydroxide ions together in solution, they are going to make a solid, right? Because that solid formation is highly favored by the constant. All right, so let's talk about the Ksp expression. All right, we've done K expressions, and we've done Ka expressions and Kb expressions. Ksp is exactly the same. So if I have some solid and it makes A of A aqueous plus B of B aqueous, the Ksp will take the same form as everything else. Noticing that's a solid, so it doesn't go in the K expression. Same rules apply. So for this scenario, Ksp will just be A to the A power b to the b power. All right, nothing new here. All right, so let's apply it to a real situation. All right, so a common question will be for you to find what's called molar solubility. Okay, and you'll be given an equation or simply just given a solid. So let's say find the molar solubility of lead iodide. All right, and you'll be given a Ksp. In this case, it's 7.1 times 10 to the minus 9. All right, so looking at the magnitude of K there, we know that not much is going to dissolve. Okay, so we write the definition reaction for this. Write the dissolution equation. Okay, because Ksp is related to a solid coming apart. So we need the dissolution equation for lead iodide. So PbI2 becomes lead 2 plus 2I minus. Right? A balanced equation is super important, okay, because now we're going to take a look at an ice table for this. Okay, so if I don't have a balanced equation, then my multiplying x won't work out, and I need it to. Right? So since solids don't go in our K expression, the solid is not going to take any part. We start with none of this and none of this because we're looking at how much solid will come apart. So we're going to take some amount of solid and put it in a beaker. Okay? And we want to find out how many ions are made. Right? And so we're looking at the forward equation here. So making ions. So at equilibrium, we'll just have x and 2x. So our Ksp is 7.19 times 10 to the minus 9 equals x times 2x squared. So we solve for x. For x to the third here. And we find that x comes out to be 1.2 times 10 to the minus 3 molar. Okay, so that means that in 1 liter, 1.2 times 10 to the minus 3 moles of lead 2 plus will be found. Right? And then we convert that to quantity of solid, right? Because we don't really care how many ions are there. What we want to find out is how much solid will dissolve in a given unit of water, right? So in this case, it's easy to take things as 1 liter because we're dealing with molarities. So 1.2 times 10 to the minus 3 moles of lead 2 plus per liter. And there's 1 mole of PbI2 per mole of lead 2 plus. Right? You have to take into account some stoichiometry here, right? Because this will tell us how many moles of PbI2 will dissolve in 1 liter of water. And it's convenient that it's 1-to-1 ratio here. Moles of PbI2. Right? So the molar solubility is 1.2 times 10 to the minus 3 moles per liter. Okay. Molar solubility of potassium iodide. All right. Now, what if you were simply asked for solubility? Solubility, as a general term, is usually given in grams per liter or grams per milliliter, or it's usually some unit of mass per volume. So I could easily transform this using molar mass. Moles of lead iodide per liter, and lead iodide is 461.01 grams per mole. Means that the solubility of lead iodide is 0.56 grams per liter. Right? This means that 0.56 grams of lead iodide will dissolve in 1 liter of water. Okay, so coming back to the ice table. All right, so looking at what we have here, I could look at this in terms of the iodine at equilibrium, but doing it with the lead makes it easier to go directly to the amount of lead iodide that will dissolve, okay, because it's a 1-to-1 ratio. But ultimately, the question of molar solubility is how much will dissolve in a given quantity of water, okay? So let's take a look at another scenario, right? So we know that our molar solubility for lead iodide is 1.2 times 10 to the minus 3. So the next question is, what is the molar solubility in a solution that already has some stuff in it? Already has, let's say, 0.1 molar iodine. Okay, and what we're going to find is that the molar solubility changes when we have something already there. And in this case, we're looking at common ion effect. All right, this is coming back to this idea. Remember, we saw that how pH changes happened when we had some acid already there, some base already there, or if we added some acid or added some base. This is the same concept. So looking at my dissolution equation, right? Think about Le Chatelier, right? If I have more of this, we shift left. Okay, so if I have more iodine already there, I'm going to keep more of this, right? More of my solid will stay solid, right? So common ion effect comes into play here, where less of the lead iodine is going to dissolve because I already have some iodine in the solution. Okay, so let's take a look at calculating what that molar solubility will be. So ice table again. Right, so we start with none of this, but in this case we are starting with some iodine already in the solution. Okay, so we're going to still approach this as things dissolving, because I want to find out how much of that lead iodide will go away. This time I have 0.1 minus 2x in this line. right? But the rest of the approach is the same. Right, and that was equal to, sorry, I lost the number. 7.1 times 10 to the minus 9 was the Ksp. All right, we go through the math, and what we can do for ourselves is assume that x is small, right? So I sort of lost track of that particular step. Because if we compare 0.1 to 7 to the minus 9, we can assume this change is small. All right, so let's rewrite this so that it looks, so we have x times 0.1 squared. Right, a lot of these types of problems will allow you to do this, because often our solubility constants, our KSPs, are very, very small numbers, so we can often make the assumption. All right, and we're going to find that x equals 7.1 times 10 to the minus 7. Right, and if we went through, we could calculate this. So this is technically the lead concentration, but this also equals the lead iodide concentration because of 1-to-1 ratio. Right, so our molar solubility means that 7.1 times 10 to the minus 7 moles per liter of lead iodide will dissolve. Or let me rephrase that. 7.1 times 10 to the minus 7 moles of lead iodide will dissolve in 1 liter. Okay, or we could just say the molar solubility is 7.1 times 10 to the minus 7 molar. Okay, now let's compare, right? So we have 7 to the minus 7 with the presence of iodine, and before we had 1.2 times 10 to the minus 3 when there wasn't anything else there. Right, so we have a factor of 4, a power of 4 difference in how much lead will dissolve with the presence of another ion there. Right, now if I were to take this same scenario with the lead iodide dissolving, and let's say I did it in a solution of chlorine, it wouldn't have any effect, okay, because the whole thing is that this is common ion effect. Right? The only way that I'm going to affect this solubility is if I have lead or iodine ions in the solution. Anything else is going to mess things up. Okay? So common ion effect is a big factor in this section of this chapter. Right? So with that, I'm going to pause and go on to the next video. Then we'll be talking about whether or not anything will dissolve, or whether or not anything will precipitate.